Right. So this is the information we learned about geometrical representation of vectors. We saw that geometrically, if we want to represent vectors, we make use of arrows, and we draw the arrows such that the direction of the arrow. Stop annotating on the board, please. Yeah. So we see that the direction of the arrow represents the line of action of the vector, whereas the length of the arrow is drawn such that it is proportional to the magnitude of the vector. Okay. So based on this, just go through this information once and note this down. I had given you an exercise to work out, so I'm putting that up next for you. Okay. So based on this, I asked you to draw vector arrows to represent the following. The vector E, which is 20 units towards east. The vector B, which is 15 units towards south. Okay. And a third one, vector C, which is 25 units towards. Now this one was a slightly complicated one, 30 degrees north of west. So just to give you a hint, north of west will be like this. If this is your north and this is your west, then this will be a direction like this. And this is the angle that we're talking about. So many degrees north of west. So now just draw a rough diagram. You don't have to draw an exact diagram in terms of lengths and all that. Okay, now from your diagram, also state the following. Find the angle between the vector E and the vector C. Okay. And the angle between the vector B and the vector C. So you have to also do these two things. Okay. So I'm just minimizing the board a little bit so that you can see the previous drawing that I've made and use that as a reference in case you haven't made the drawings. And if you made the drawings, then just yes, good. Yes, that answer is correct for you. Okay. And Aman, yes, your answer is correct. Very good. So Yash and Aman, both your answers are correct for the angles for part A and part B. Yes, we're giving correct answers, most of you. Okay, so let me work out the first part for you. Let's draw the vectors actually. Okay. So now, first of all, let me draw what is called a reference frame, okay, so that we have some idea about the general directions. So this is, suppose, my general reference frame. So this represents the north direction, let's say. This represents the east and south and west. Okay. So according to this now, how should I draw a vector E? It should be pointing towards east and it should be 20 units. So let's say I just represent it here. So now one thing you have to be sure to understand over here is that So this is 20 units. And I don't even know what unit it is. It could be newtons because I could be talking about force. It could be, kilometers or meters if I'm talking about displacement. It could be meters per second if I'm talking about velocity, like that. Okay. Now, before I start with others, one thing you have to understand is that this vector is completely movable. If I, instead of drawing it here, if I draw it here, there's no problem. It's still the same vector. If I draw it here, it's no problem. It's the same vector. If I draw it here, it's no problem. It's the same vector. Every time it represents the same thing. It represents a vector of this thing of magnitude 20 units and pointing in the direction of east. As long as I don't twist the direction of the vector or I don't twist the length of the vector, okay, it's going to represent the same thing. So the vector can be drawn from any point. It need not be drawn always from the origin of my system. It can be drawn from any point. Now, in comparison to this, how will the vector B look, for example? The vector B will look like this. It will look like a vector which is shorter in length because it was only 15 kilometers, but its direction was towards south. So B will look like this. So just I am making a rough estimate that if this is 20, then there should be 3/4 of this because it represents 15. So if I'm making a very exact diagram, then whatever this length L is over here, this length should be 3/4 of that length. Okay, but as I said, that's not necessary to do exactly over here because I'm already labeling it. I'm saying that, okay, this is 15 units and this 20 units. So that is done. Okay. Now let us come to the more tricky thing about the third vector, which we have talked about, which is the vector C. Okay. Now, where is the vector C line? Now, since it's given in degrees with respect to northwest, let's draw it from here. It will be easier to understand. So it should be slightly longer also because it's 25. So let's say this is the vector C. Now its length should be proportional to 25 units. But more importantly, its direction is 30 degrees north of west. Okay. So according to the information I've given you in the question, this is how the diagram should look like. Okay, now we will have to relate these in a slightly different manner to understand the part A and part B, how to find the angle between them. So I'm coming to that. Okay. So now let us talk about the second part where we are calculating the angles. Now to calculate the angles, what I will do is I'll redraw this diagram, or in this diagram only I'll reposition my vector so that it's easy to compare them. Okay. So it's easy for me to do this because I'm using a whiteboard, but literally you can redraw a diagram where you do this. So you place A and B such that maybe it's not so easy after all. Okay. Okay. So my vector A, I'm just placing it over here. Okay. Now similarly, I'll place my vector B also over here. This, so now because I've placed them from a common origin, it's very easy to analyze what the angles are. So you can see that from the direction of B to the direction of A, if you switch, you're rotating by 90 degrees. Whereas from the direction of A, if you switch to the direction of B, you're rotating by this angle. Let us say this is alpha, and this angle is how much? It is 90 plus 60 or 150 degrees. Similarly, if you switch from the direction of B to the direction of C, you're going like this. Okay. So that angle, let us say, is beta, and that angle you can see is how much? 90 plus 30 So it is 120 degrees. Okay. So this is what will help us solve the second part of our question. Okay. So second part, we wanted to find the angle between A and C and the angle between B and C. So as you can see, the angle between A and C is nothing but alpha, which is 150 degrees. Okay. Now you can also say that it is this angle, it's the other way, 360 minus 150. So that's how much, 210 degrees. Okay. But we don't use this angle, we use this one because it's more convenient, the smaller of the two angles. You're understanding my point? That this is like this and this is like this. So this angle, if it is 150 degrees, then this angle is 210 degrees because the total is 360. So that's fine. I can use this also. But generally speaking, we go with the smaller of the two angles. So it's easier to understand. Okay. And similarly, the B part, the angle between B and C, we'll take the smaller of the two. This is 120, this side would be 240, but we'll use this angle, which is 120 degrees. So this becomes my answer to the second part. Okay. So, given two vectors at random positions like this, if we are ever confused about how to find the angle between them, we can redraw them from a common origin, and from that we can figure out the angle between them. Okay, so next up, so hope this is clear to all of you and you got the answers yourself also. Okay, now next up, I'm going to give a reverse. No, making a triangle right now is not important for us. Okay, the important thing in this diagram so far is to just understand the angle between the vectors. Okay. So therefore, right now we will not be making a triangle. The vector triangle is made for a different reason. It is made for doing vector addition, which we'll understand very soon. Okay. But anyway, now the next example is the reverse of this. I am giving you three vectors in the diagram, and from that you have to tell me the relationship between them. So suppose in this, I am giving you the vector E. Like this. Okay. So the vector E is exactly like this, and it is, let us say, 10 units. Okay. Now in the same diagram, I am drawing the vector B like this exactly. Okay. And like this. But this thing is unknown, whereas this angle is 45 degrees. This angle. Okay. And in the same thing, now I am giving you vector C. Which is, let's say, like this. And again, its magnitude is unknown. Okay. But this angle is unknown. Okay. So you have to find in this diagram, firstly, the magnitude of the vector B and the magnitude of the vector C. Okay. And secondly, you have to find the angle between A and B again, and B and C. Okay. A and C you can directly see is 90 degrees, so it's no big deal. Okay. So just with respect to my XY coordinate frame, now this need not be north, south, east, west and all. So just try this out and assume my diagram is very correct. So you can count the boxes in my diagram and actually come up with the solution. You can literally count the boxes. Treat my whiteboard like a proper, what we call it, the proper graph paper kind of. Yes, Aman correct, Rushant correct. Okay, so let's understand how we will do an exact calculation of the magnitudes here. Most of you got it correct who have replied to me. Okay, so see, if this whole thing is 10 units, this is how many? 1, 2, 3, 4, 5 boxes. So that means one side here is basically of how much length? One side over here, or just what if I just, so you can see that this side length from here to here for one box, in terms of my vector notation, must be how much? It must be 2 units. Okay. Similarly, this is also 2 units in length. How I'm getting this information? Because I'm using this reference. Using this reference, I'm understanding that therefore this is also 2 units. But this also means that now, very interestingly, this diagonal length, or for that matter, this diagonal length, they are how much? They are 2 root 2. Just use your knowledge of squares. The diagonal of a square, this is 2 root 2 units. So that's how we'll understand the magnitude of B. So it's a little bit more technical than you guess. Okay, that's why many of you did not get the magnitude one part correct. Okay. So you'll see mod B should be equal to how much? Now see how many diagonals mod B has. 1, 2, 3, 4. So it is 4 times the length of each diagonal, which is 2. So magnitude of B is in fact 8 root 2. Or approximately you can say 8 into 1.4. But this is fine. You can just leave it as 8 root 2 units. Whereas magnitude of C, you can see, is much more straightforward. It is 3 units downwards, so 3 into 2, so 6 units. So this is the answer to the first part. Okay, so magnitude of B, interestingly, is not 8 units. It is 8 root 2 units, because it's not about number of boxes. It's also about whether you're going diagonally in the box or you're going like this. So we are making use of that. Okay, and then the angles are pretty simple, as you can see. If this angle is alpha, this is the angle between A and B. Yeah, and in this diagram, if this total angle is beta, use a different color for it. So this total angle from here to here, this is beta. So these will become the answers to your second part. Between A and B, you can see from that diagram, the angle alpha will be 90 plus 45 or 135 degrees. And similarly, between B and C also it will be the same. The angle beta, that's also 135. All right, so I'll just leave you a few seconds with the solution of this. Okay, so make sure this is clear. Yeah, Aditya, I got your point, so it's okay. Right. Yeah, so Aditya, to understand, sorry, not Aditya, Atharva, to answer your question, Atharva, about the magnitude of the vector B. So if you look at the vector B's diagram that I've drawn, it is basically in which direction? It's along the diagonals of those squares. Okay, so I'll just magnify the picture to explain better again. Okay. So you can see that B, the way it is drawn, see it is exactly along the diagonal of the squares because this angle is also given as 45. So you know that it's how many boxes? It's 1, 2, 3, 4 boxes. But each box, which direction you are covering? The diagonal, not the side length. So now coming back here, if the side length of the boxes are 2 by 2, then what about the diagonal? It is 2 root 2. No? So the diagonal is 2 root 2 units. So coming back to magnitude of B, the magnitude of B is how much? It is 4 diagonals, 4 box diagonals, 4 times the diagonal of each box. So that is why it is 4 into 2 root 2. Correct? So that is the explanation of this. So if the angle is of other measure, then we'll have to use some other way of solving the length. So for example, if the angle was 30 degrees or something, you would have drawn a rectangle and calculated the side length of that rectangle. So by measuring the boxes for the width and the length A and B, let's say, or L length and width B of the rectangle, you would calculate the diagonal length as square root of L square plus B square. What I'm trying to say is that if we have made an exact diagram on a graph paper, like I've done over here, we can always use the measurements on the graph paper to actually calculate the magnitudes. But typically we don't do that. This is just for demonstration purpose. We typically just make a rough diagram on pen and paper without even using scale and protractor and all. We just use freehand drawing. It's just for the representation purpose. Okay, so let's move on to the next thing. Now that we have understood quite a lot about the representation of vectors and how that is used to understand the relationship between two vectors using the geometrical method. Now we start the next thing with vector operations or algebraic operations on vectors. So you can understand this as vector operations. So the first type of vector operation we will study is a very simple one. We will see multiplication of a vector by a scalar quantity. Just a moment, people. I will just stop the whiteboard for a moment and reshare because it's lagging right now. Just give me a moment, people. I will be back with the whiteboard. Okay. Right, now just about the vector operation. So the first type of operation we'll see is multiplication of a vector with a scalar. And the most famous equation, one of the most famous equations, Newton's second law, applied for a rigid body or for a particle of mass m. And this one. So you can see right hand side, what you're doing is m is mass, which is a scalar quantity, whereas e is acceleration, which is a vector quantity. So in the right hand side, you are actually multiplying a scalar quantity mass with the vector quantity acceleration. So let us see what this operation actually means in terms of vector algebra. Let's understand what this means. Okay, so we generally denote it like this, that suppose we say any vector b is equal to any scalar n multiplied by any vector e. So here n is a scalar. Okay. So let us look at three possibilities here. Okay. The possibility one is that n is a positive quantity. Like in the case of mass, there is no such thing as negative mass, it's just a magnitude. So for example, if I say that the vector b is 3 times the vector e, so you can see that n is equal to positive of 3. Okay. So what that means is that the magnitude of the vector b will be 3 times the magnitude of the vector e. Okay. And b's direction is along e. It is the same direction as e. Or you can say it is parallel to the vector. Okay, so that is the first case. So how we represent this in a diagram would be something like this. Suppose I am given the vector e is like this. This is the vector e. And I tell you that the vector b is 3 times vector e. Okay. So this is how I represent the vector b. It would have to be parallel to this, but it would have to be 3 times in length. So this would be my vector b, which is 3 times vector e. That means this magnitude of b, this length, would be 3 times e, this length, compared to this length here, which was e. Okay. And also they are parallel, so that means they are along directions which are parallel to each other. They are along the same direction. Okay. So this is the meaning of multiplication with a positive quantity. So I am just giving you some little bit of time to note down this first case of when we multiply with a scalar quantity. Katie, come in. Katie. Oi, Popo, come in. No. Katie, hey, don't do that. Alright, so they should be pretty self-explanatory. You could also have an example like this where, vector c, let us say, is 0.5 times vector e. So it can be a fractional number also. So this will mean that magnitude of c is actually half of the magnitude of e, or 0.5 times the magnitude of e. And c is parallel. Could also have a situation like this. Right, so that's the first situation. Okay, now the second possibility is that the scalar quantity we are multiplying with happens to be negative. That will not happen in an equation like f is equal to ma, because m over there is a mass which is having only magnitude and no algebraic sign. But it can happen in other cases, like for example, later in the chapter of electrostatics in 12th class 12, we'll see that the force acting on a charged particle is given by the equation q into e, where q is the charge of the particle and e is what we call the electric field. So their electric field and force are vectors, whereas charge is a scalar. But as you know, charge can be both positive or negative. So if we have the equation like this, F is equal to charge into electric field E. So here Q is charge. So it could be both positive or negative. So that's how this comes. Okay. So if we have in the equation B is equal to N times A, N is a negative quantity. Okay. So for example, suppose B is equal to minus 2 times E. So N is negative, as you can see. So what this means is that the magnitude of B will still be 2 times the magnitude of A. When I'm looking at magnitude, I will not say minus, because magnitude does not have algebraic sign. Okay? So remember, magnitude is absolute. or it is what we call a mod quantity. It's a modulus type of quantity. So there's no sign involved here. But the minus sign will now show that B is opposite in direction. To A. Or by opposite, we can also say it means it is anti-parallel. Okay. That is what. So this example would now look like this. If I'm drawing the vector E, as let us say this, just for variety I'm drawing it here. This represents the vector E, and it has a magnitude which is this length. Now in comparison here, B could be drawn like this. I could draw it like this also over here, or I could draw it somewhere here also. It doesn't matter, it's one and the same thing. But the important thing is, whichever option I take of drawing, B is at 180 degrees, it's opposite in direction, and this length of B, that is 2 times the length of B. So this diagram now represents the information that the earlier equation was giving us, that we are multiplying a vector with a scalar quantity, but that scalar quantity happens to be a negative quantity. And in case you are wondering why I have said 3 cases, because we already covered positive or negative, we have the very interesting unique case of when that n is 0. Okay, so we will see next what happens when n is 0. Alright people, so hope this is clear. Okay, now let's move to that. It's in mathematics, these kind of cases called a trivial case because it's actually very simple. But for the sake of completeness of definition, if you ask yourself, okay, n can be positive, n can be negative, but what about if n is 0? So we have to cover that case also. So for that we have to discuss something very interesting called a null vector. Okay. So the third case is if we say B is equal to n times A, but it's a unique case of n being 0. Then what happens is B becomes something called a null vector. It's the same thing as 0 only, but now it's in vector notation. So this thing is a new definition for us. It is called a null vector. It means it is a vector of magnitude nothing. So magnitude 0. So it's a very special type of vector, the null vector. It's a vector which has 0 magnitude and therefore no significant direction. And why we need to define the null vector separately? Because I cannot write an equation like this. Writing an equation like this is wrong. Why it is wrong? Because this side is a scalar, okay, and this side is a vector. So I have to stick to the laws of vector algebra. So when I write a vector on the left hand side, it must be supported by a vector on the left hand side. Yeah, an example of a null vector is if we subtract the same vector from itself. So that is a null vector. Or we multiply a vector with 0, that's a null vector. So for example, if we make a displacement like this, and then again make a displacement back like this, So what is our resultant displacement? It's 0. But remember, displacement is a vector quantity, so we have to represent it by a vector and not as a scalar. So those are like the practical applications of null vectors. Okay. So this is just a trivial case, as I was saying. So that covers our multiplication of a vector by a scalar quantity. Now we come to the next important thing, which is very important. One of the important formulae as we go along in future. We'll do the derivation of that formula. So we will do addition of two vectors. And the method that we use over here, it is called the triangle law of vector addition. Okay. So this is one of the staple principles of vector algebra. It's a very important milestone in your understanding of vectors. Okay. So how do we do the addition of two vectors? Now, first of all, you have to understand one thing over here, that we can only add two vectors when they are expressed in same unit or they represent same physical quantity. So two vectors can be added only if they represent identical or the same physical quantities. Okay. Or in same unit. Okay. So for example, we cannot add a force in newtons with a displacement in meters. We can only add force with force. We can only add, okay, so that's important. That's very simple. Yes. Okay. Now let's come to the actual statement what we mean. Okay. So suppose we have a vector E given to us like this, and any general vector E. It need not even be along the x-axis. So this is the vector E. And we have another vector B which is given to us, which is like this. Right. So these two vectors are given to us such that we have information about their magnitude and direction. Students, unfortunately, will have to take a. My system for some reason has again. So I will just have to quickly reboot my router because the whiteboard is not online anymore. So two-minute break for everybody. You can stay online only, but just take a 2-minute break. Right. So what we saw is that if two vectors are known to us in terms of their vector arrows, okay, so we know. Now let's just say for argument this I've drawn along the x-axis only. So this is my vector E, and then in some kind of general direction like this, I have drawn another vector B, and I want to find now what is called the resultant sum. Resultant, or this can also be called the sum of E and B. So algebraically, that would be denoted with the symbol R to stand for resultant, okay, and it would be written as the vector operation A plus B. So we use the plus sign, the normal plus sign for this operation, addition of vectors. We use the symbol plus only, but now we are applying the symbol between two vectors. So the laws that we use for that actual operation are going to be different. That's why we are studying the new operation vector. Okay. So how do we actually do it given these two arrows. The thing is, let's think logically that if these are displacements, for example, what I mean by this operation, I mean the net displacement after completing a displacement of A followed by a displacement of B. So this is very much like the first example we are understanding today when we are talking about what is vector and what is scalar. So what we have to do is think that this is the point from which I'm starting this. So this is my initial point. Okay. And now I'm making a displacement of A first. So what I'll have to do is I'll have to pick up this arrow and place it over here. So here, just for your reference, I will, instead of doing that, I'll draw another arrow. But remember that this arrow I'm drawing is identical in all respects to that other arrow. Okay. So this arrow now represents the vector E. So this is where I end up after completing the displacement E. But now I'm actually making a net displacement, which is the resultant of E and B. So I'm not stopping at this point. I'm making the further displacement of B. So I have to pick up that arrow, the one that represents B now, and place it over here. So again, keeping in mind that this is an identical arrow to the one on top. Okay. So this is where I would end up now after completing the displacement of E followed by the displacement of B. So whatever location I'm at now, that becomes my final location. Okay. Now you might say what sense this makes in terms of forces and all. We'll come to that, don't worry. Just think of them like displacements for the moment because they are the easiest vectors to visualize for us. So by the definition of displacement, the resultant of these two is becoming which one? This is becoming. So now as you can see, my task has become a geometrical task that I know two sides of a triangle. Okay, and I have to find the third side. Okay, but of course I have to be mindful of that fact that in this triangle, this is the direction of A, this is the direction of B. So here this angle theta is the angle between A and B. Okay. And suppose I denote, so the magnitude of the vector E, I am using the short form A scalar for it. The magnitude of the vector B, I am using the short symbol just B scalar for it, and the angle between A and B. That is why we did that exercise of calculating angle between. Okay. So angle between the vectors A and B, that is denoted by theta. So these quantities are given to me. Okay. So given these things, suppose I know the numerical value that mod A is some 10 units, mod B is some 5 units, theta is some 30 degrees or whatever. Then I want to find out what all. I want to find out the vector R. So in other words, I want to find out the magnitude of that vector R, how much that is. And I want to find out this angle which will give its direction. So let's say that angle is alpha. Because I need the complete information about R. I don't need just the magnitude, I need the direction also. So as you can see, it has become a problem of trigonometry now. Everything to do with triangles is trigonometry. Though till now you studied trigonometry of right angle triangles, but you will see how trigonometry can be extended to study any given triangle. Okay, and by applying the principles of trigonometry, we can get the third side of the triangle because we are given two sides and we are given what in triangle language is called the exterior angle of the triangle. So given the exterior angle and the two sides, how we can find the third side? Now that is the principle we apply. So what we'll do next year is now we'll treat this like a geometry problem. Okay, so as a geometry problem, we have got this side which we want to find out R in magnitude. We have got this side, what is supposedly given to us, which we can understand that this is capital E from here to here. Now the third thing which we know about the triangle is this side, which is actually the vector B with the arrow, but right now I'm only interested in the side length. So this is B. And one more piece of information that I have about this triangle is this. If I just extend this line, so in this diagram, the additional information I have is I know this angle theta. Okay. So A is known, B is known, theta is known, and we have to find out the magnitude of R. Let's say that is our problem. Okay. So how do we apply trigonometry here? So the first step we do is we know definitions of sine, cos, and tan in terms of right angle triangle, and I don't see any right angle triangle right now, and not unless theta is 90 degrees, and that's a special case. So to make a right angle triangle, what I do is I help myself by dropping a perpendicular. Okay. So this is also a helping line for me, so I'll just go to the dotted line. And now in this triangle, let's say this side is x and this side is y, and these are pretty easy to calculate because you can see that you have this triangle which is a right angle triangle. So I'll just take out that triangle separately and you'll understand what's happening here. For that smaller triangle now, I have this side x, I have this side y, okay, and I have this side as what? B. And in this now, you can see how we've labeled the diagram is this base is x, this angle is 90, this perpendicular is y, and this angle is theta. So all I've done is from this diagram, I've picked out this right angle. Okay. So before we continue forward, let me just see how we show you how we have converted the original diagram where I was given just the two vectors A into A and B into the vector resultant diagram. Okay. So I was given these two quantities, and from that I was asked to find out this. So what I did is to sum them up, I placed the vectors like this as if they are displacements. So it's a displacement of A followed by a displacement of B. And then I understood, okay, what is the resultant displacement? It is this one R. Okay, so I did that. And next, now I want to solve this thing. In this triangle, I know the value of capital A, I know the value of capital B, and I know theta. But what I have to find? I have to find the magnitude of this side, that is R, and I have to find this angle. So I'm just taking a relook at that triangle. Okay, just imagine that this triangle is exactly the same. So in taking a relook at the triangle, I'm extending the line of A and I'm dropping a perpendicular from the head of B. So I'm getting this right angle triangle. Okay. This right angle triangle which I've drawn below. So now let us apply trigonometry to this. Okay, so you can see y upon b is nothing but perpendicular upon hypotenuse. So it is sine theta by definition. And x upon b is nothing but base upon hypotenuse. So it is cos theta. So my two unknown quantities in this triangle, which were x and y, they now become b cos theta and b sine theta. So this is the first analysis of trigonometry that I'm doing. That this triangle over here is redrawn over here, and I'm applying trigonometry to it to find out this unknown length x and this unknown length y in terms of two known quantities, which are magnitude of the vector b and the angle theta between them. Okay? So this is the first step. Just make a quick review of this, then we'll come to the next step. Remember, our ultimate goal is what? We want to find this side. So we are just using x and y to help us. Okay? We still have to develop the formula for r. I will just take another 10 minutes or so. In any case, unfortunately, our start was delayed, so I don't think any of you have a lecture at 2:30 or anything. So just checking for your messages in the meantime. Okay. So now see what I'm going to do in the next step is I'm going to look at this larger triangle. Okay, so I'm going to redraw the diagram where I understand the larger triangle. So the larger triangle is now like this. This side is A. Okay. Then we have so this was A, and then we had this little bit over here, which was X. Then we had this perpendicular over here, which was Y. Okay. And we had this side's resultant, which was actually our R vector. This was our R vector, which we wanted to find out. So the length of this line is what we are interested in to begin with, because that's the magnitude of the resultant. That is mod R or you can also say it is magnitude of the vectors sum of A and B. That is this side, okay. And in between, of course, we had the vector B over here. So that's not so important for me just now. More important for me is that this part is X, this part is Y, and the angle in between here is 90 degrees. So this angle is 90, right? This section is X, this section is Y. And what about this section here? This is E. That's the magnitude of the original vector E. So I have E over here. So now look at the larger triangle that I'm talking about, this right angle triangle, this whole one that I've drawn. This side is R, this side is A plus X, and this side is Y. So apply Pythagoras theorem here instead of trigonometry, and you can see that the hypotenuse should be square root of base, which is A plus X whole square, plus perpendicular, which is Y whole square. Like this, okay. And now substitute the values of X and Y, which I've seen earlier. So go back to the earlier diagram and see that X is equal to B cos theta and Y is equal to B sin theta. So make that substitution over here. Substitute X and substitute Y. So next step that we get over here, this becomes how much? This becomes square root of A plus B cos theta whole square plus B sin theta whole square. So I'm sure these steps will be clear to all of you. I'm just minimizing it for a moment for you to see. And once the steps are clear, now you can just algebraically simplify this a little more. Okay, so we can use the whole square formula and algebraically simplify this a little more, and that's how we'll proceed. But before that, just make sure that you understand geometrically what we've done. Right, so I think this should be clear to all of you. Yeah, to answer one of the queries, the magnitude of the vector A is nothing but the length of the arrow. So the length of the arrow of vector A, see in the original problem, I was given these two arrows. Now these two are given to me, so I know their lengths. So the length of this arrow represents vector A. The length of this arrow B represents vector B. So they are known to me. And I have also drawn them earlier. So from the diagram, I can see what the angle theta is. So that is the whole point, that we are given these two arrows A and B, which represent the vectors A and B. So from that, how will I get information about this thing, which is the resultant of A and B? How will I get information about the resultant? Okay. So that is what we do. All right. So let's just complete the algebra here. That's all. So next step, when we expand this, you can see this will become square root of A square plus 2AB cos theta plus B square cos square theta. So this is that first term, and then from the second term we also have B square sin square theta. Okay, so as you can see, this is what this step is resulting in when we expand this and expand this. Okay, now you use the popular common identity that cos square theta plus sin square theta is unity for all angles, and that is basically Pythagoras theorem. Base square plus perpendicular square upon hypotenuse square is unity. So we get the formula that R is equal to A square plus 2AB cos theta plus B square. And for whatever reason, more popularly in books and all, it is written in this order, that this resultant is nothing but the magnitude of A plus B. Remember, that is what the magnitude of R was. And that is given by this simple formula, that it is square root of mod A square plus mod B square plus 2 times the product of magnitudes of A and B, mod A into B, into cosine of the angle between them. Okay. So this becomes the statement of what we are looking for earlier. This becomes the statement of triangle law of vector addition. Okay. That given two vectors A and B, that means I know their magnitudes and I know the angle between them. This is how I can find the resultant's magnitude, that is A plus B's magnitude. And of course, we have to still find the angle alpha, which was the direction of the resultant R. We'll come to that also, but that's also almost done because it's there in the triangle. But first point is you just understand the algebra over here and see how we've simplified this relation starting from this triangle. We simplified it from the base square plus perpendicular square is hypotenuse square, this formula, how we simplified it to this now. So as you can see with this formula now, our calculation of the resultant becomes formula based. Now, if I just give you A's magnitude is 15, B's magnitude is 20, and the angle between them is 60 degrees or 45 degrees or whatever, all you have to do is substitute in the formula and you will get the magnitude of the resultant. That is the whole point of the triangle law, that it gives us a formula where we can do direct substitution. Alright, this is done. Okay, now the next thing is we also wanted to find out, subtraction will come later, don't worry. We will do things one step at a time. So coming back to this diagram, we also wanted to find out this angle. This angle was our alpha, because this is the angle that the resultant vector is making with respect to the vector E. The vector E as a direction had an arrow in like this over here. So E ka direction ye hai, resultant ka direction wo hai. So the angle between E and the resultant, that we are labeling as alpha, and we also want to find out the angle alpha. So this is the direction of the resultant, this is the direction of E, and we want to find out the angle between them. That's this one. This vector and this vector, we want to find out the angle between them, which is this one. Okay, so let's apply trigonometry again to this, and you can see that in this diagram, tan alpha is perpendicular upon base. So let's use that formula. So additionally, we also have tan alpha is perpendicular, which is y, upon base, which is a plus x. And we just saw earlier that x is replaced with b cos theta and y is replaced with b sin theta. So we have tan alpha is equal to b sin theta, which is y, upon a plus b cos theta. So this becomes our secondary formula. So I just put it below over here so that both the formula are in one place in your notes. So tan alpha is becoming this formula, b sin theta divided by a plus b cos theta. So in both the equations which I put up now in boxes, you can see the right hand side consists of known quantities, so direct substitution, and the left hand side is the unknown quantity. What is the magnitude of a plus b and what is the angle alpha? So tan of that angle is given by this. So together these two actually constitute the complete statement of triangle law, that the magnitude and the angle of the resultant vector is given by this. Okay, so this is where we conclude the first lecture of vectors, and I will now just give you some basic information about the reference, and eventually I'll be giving you a worksheet also to try out some questions using this. And as a look ahead, we'll be doing lots more operations on vectors, not just addition of two vectors, but we'll also see how to add multiple vectors. We'll see how to subtract vectors, and we'll also see how to calculate products of vectors. All right, people, so that almost brings today's lecture to a conclusion. So just about a couple of things. For reference, okay, use the lecture notes. Which I will be sending you, whiteboard notes. Okay, use that, use your own lecture notes. Okay. Okay, and use the Iitians Hub physics module And the name of that module for vectors is going to be this one. It is Mathematics for Physics. The name sounds a little contradictory, but actually the full name is Useful Mathematics for Physics. So actually what we are studying right now is vector algebra. So it's part of mathematics, but it's useful for physics. That's why it comes in your physics section. So we use the Iitians Hub module. And plus I will also be giving you a worksheet. One for vectors, which will be your homework until next time. So once you revise my lecture notes, you can actually directly jump into the worksheet problems. It's no issue there. But you can also study the initial part from the module, where you will find the same kind of things described over there. The definition of vectors up to triangle law of vector addition. You can do that part. So that's it about today's lecture, people. Hope everything is clear to you. This is a very critical part of our studies, vector algebra. And we'll very soon, when we jump into things like motion in 2 dimensions or kinematics in 2 and 3 dimensions, or later when we come to Newton's laws and application of F is equal to ma or dynamical equations, etc., we'll see that we are constantly applying the principles of vectors like we are doing over here. Okay, so that is going to be the reason why we are studying vectors in detail first, is because in order to start with those chapters of physics like motion in 2 dimensions and dynamics, we have to have a background in vector algebra. So that's the reason why this is the fundamental first chapter. Okay, so that's it from me, guys, and hope you've enjoyed the lecture. I've enjoyed bringing it to you, and stay safe and all the best.